Hmm. Well, we have done now we have a tool for computing stress through the depth of a beam. Depth, longitudinal stress, which is normal stress on any cross section of the beam, that can be computed. Now, as you know, most of the beams will not be subjected to pure bending. So we have developed a theory for pure bending, and in practice the beam will not be generally subjected to pure bending. You will always have a beam. So we will now say bending of beam. This is the title of the today's lecture. See, if you have a beam, again for the sake of simplicity we are taking simply supported. If you have, let us say, so this beam, the bending moment diagram is and the shear force diagram will be so this is shear force or V diagram. There is no axial force in this beam. So this is your shear force diagram. This may not be equal L by 3, but it is L by 3, L by 3, L by 3, all the three. You diagram, everything is okay, or is there anything wrong? Signs are okay. Why it is negative here? As per our sign convention is on any cross section on a positive x, this is our positive shear, this is our positive. On a negative face, this is our positive shear and this is our positive moment. So check up whether whatever we have drawn is right or wrong. This is correct. Okay. Reactions are P and P. Although I have not removed the support, but reactions are here above the reactions will be P. So at any cross section here, any cross section here, P and P, so P here will be like this, and moment about this will be like this. So moment about this, P into this distance x, so that will be this. So in order to balance this, what is the diagram, what is the moment here, what is the sign, it will be like this. So this also is negative, this also is negative, because upward shear on the positive face is positive, and a clockwise moment on the positive face is positive, which is going in y direction, while this moment will be going in negative y direction. Is it okay? So both of these are negative, so that is why we have drawn this negative here, shear. I mean, as per this convention. Somebody else are in book, it may be the other way, but we are following this. So you see here that this, now the entire length of the beam is not subjected to pure bending moment. Which portion is subjected to pure bending moment? Only the central portion, L/3. This is only subjected to pure bending. There is no shear here. So this L/3 in the central position, because here shear force is 0, while here it is changing, here it is constant, moment is linear, so dm/dx will be a constant because it's a linear variation. So rate of change of moment is a constant slope. Constant slope is this. Here also constant. This is positive slope, this is negative slope. Is it okay? So you should understand, because V is given by dm/dx. So that should come out to be true. So you will have always situation where the entire length of the beam will not be subjected to pure bending moment, and therefore whatever we have developed is not truly right. So we will now assume, let us assume, now here one more assumption, that even under this case, whatever we have derived is right, will hold good. So assume 2. Sorry. Sigma x equal to that means we are assuming that still we can find out the stresses through the thickness of the beam by this formula. There will be some approximation we can find out later. So that means now this formula will not be exact, 100% exact, but it will be it will be. So now what you had raised in the beginning is, sir, you are using the second assumption that transverse normals, this is the cross section of the beam, this is the longitudinal section of the beam, and this is the neutral axis x. So you had said that this transverse normal, originally this is 90 degree, and after bending, after it gets deflected, after it gets bent, let us say the same section, although we are drawing side by side, but it is the same length. This will get oriented something like this. Displacements are small, so although it is shown as if it is too much, but actually it will not be happening like this. It will be all small quantities. So we are assuming that this normal will still remain like this, and this angle will still be pi by 2. So now this is because there is earlier shear stress was 0, pure bending. Therefore, you could use Hooke's law and you could say that shear strain will be 0. So this was true because this is nothing but shear strain, 90 degree. Now it is not so. Now shear stress is not 0. Shear strain will be there actually. There will be, that means this will be slightly inclined, not necessarily 90, but we are assuming this to remain 90 degree. So we are assuming here that this Z, we are assuming that gamma xz is 0. This means gamma xz is 0, shear strain is 0. This is a Kirchhoff assumption. This is called Kirchhoff, Kirchh. Spelling you remember. It is not CH. Many people write CHOFF. It is not. It is KIRCHHF. Kirchhoff's hypothesis. So this is, now we are really assuming this. So this is a Kirchhoff hypothesis. So we are assuming that this holds good now. Holds good. Okay. If you assume this, then we can proceed further. So in general, if I take a beam element of length dx, then it will be cover. Same diagram. So this is Now let's say at a distance z, a fiber at a distance z from the neutral axis, what is the stress? So here this will be some sigma x at x plus delta x. Here will be sigma x, and this will be at x. Is it okay? Can you find out the value of sigma x? Can you find out the value of sigma x at x? At x means at section x. This section is at a distance x. What should we do? Yes, please. Can somebody tell me what is the value of sigma x at x in terms of the quantities that are shown here, in terms of the forces that are acting? Moment is there at the cross section, moment m. So mz by I. So moment into z by moment of inertia. This I is about yy. You know, we are not writing. This moment also is about y-axis. Moment also is about y-axis. This also is about. So that must be remembered. So although we are not writing, but then this is this is all right. Sigma x, yes, can be found out by this. What about sigma x at x plus delta x? It will be moment plus dm into z by I. Let me take out this. Let me take out this top portion. I will, for the time being, I will not consider this load, because you saw that moment can change. Moment diagram was changing shear even without load on the top surface. It not there was a load in the concentrated at a central point or at some point, but moment was. So let us say this is not there for the time being, and let me draw this top free body diagram of the top portion. Cut the beam. I am cutting the top slice. I am cutting. So top slice, if you are cutting, then what is happening here? it will be stress sigma x is acting. Here again some sigma x is acting, I mean at cross section x. And when you have cut this, then here you have shear stress. You will be because there is a shear force, so there will be some shear stress that will be at this point, and then we do not know the variation, so there has to be some shear stress. Vertical on this plane, shear, what is the positive shear? V is going upwards, so the shear has to be, shear stress means V divided by area of cross section. V has come by, how do you get AV? By integration of shear stress over the area. Integration of shear stress over the area, you get the shear force. So there will be some shear stress distribution, there will be normal stress here and here. And what about this point here at the bottom? Bottom will be what? Yes. Why? Why it should be like this? What is this? Huh? What is this? Tell me. It is shear stress. Why the direction is like this? This is a element. This one is going upward, so shear stresses are always complementary. So if it is going upward, it has to be like this. So that here automatically, see, this arrow and this arrow is, here it is, both the arrows are going away at this corner. So this diagram is, so this is the shear stress at that level, at a distance z. This one is at, see, this diagram is important. This is at a distance, this distance is z. So is there anybody who has not understood this diagram? This is the free body. See, once you take a slice of the top, you cut it, separate it. So I have drawn the free body diagram of this top slice of the beam. The reason is I want to find out the value of, I want to find out the value of shear stress at that particular point. So this is the free body diagram of the top slice. Here it is a free surface. Top is, here it is a free surface. No stresses are there. I told you, let us assume that there is no load on the top here. So this is a free surface. So on this is a normal stress, this is a shear stress, this is shear stress, this is a normal stress, and here there will be only shear. And why there should be only shear? The reason is, can there be also normal stress? Yes. Namrata? Here normal stress. I can also have a normal stress. But I have told you right in the fourth assumption in the beam theory, we have assumed that normal stress is a very small quantity compared to this stress. This stress is sigma x. This is sigma x. This is sigma x. So this one we are neglecting, that normal stress is a small quantity. Because here it is 0. So variation of that normal stress will be very small. So that is not, we are not taking normal stress. Sigma z is assumed to be equal to 0. Not exactly equal to 0, almost equal to 0. Because if you take exactly, there will be problem. Okay. So let us try to take the free body. This is the free body diagram. This is in a state of equilibrium. This is small element. So let us call this as sigma. What should we say? This is small. Let us call this as del. I am just trying to see what value should I call. Del F. This is Z surface and this is in X direction. You see, this area, top area is A1. This is also A1, area of cross section. Now let me sum all the forces. Sum all the forces in X direction. They have to be 0. Come to this face. So sigma X into dA, integrate over area 1, and this is computed at section, well, okay, X, alright. Direction here is negative. It is in minus X direction. This is, if I integrate this, this will be in this direction. X positive is this direction. So I am giving a negative sign here. Then this force. See, bottom force. This is, I have given not stress. This is Fzx. What is F? F means force. What is Z? Z is the normal. Normal to this surface is Z direction. Negative Z direction. Z downwards. So it is Z. And what is the direction? X direction. This is in negative X direction. So this is, I have just given Fzx. So this is the total force on this surface. Total force comes because of stress multiplied by the bottom area. Bottom area will be this length dx multiplied by the width of the beam. You understand that? Bottom. Okay, so that is the total. So here minus delta F Zx, then plus integral yes, this is all. This must set equal to 0. If you can do this, then this will be right. Is everybody agreeing with this? Because this is the crux. If you don't understand this, you will not follow the next step. This we have taken. See, this beam has a cross section also. Let us say it is a rectangular cross section. So this has got a cross section at a distance. This is y axis. So at a distance z here, this is the cross section. This is the cross section. So what is this? This is the B width. B is the width which you are not seeing. This is longitudinal section. This is the cross section, transverse cross section. In y direction, this is z direction. Yes, this will be z. This is also z. If there is any doubt, you tell me. This equilibrium condition will hold good. Is this correct? If this is correct, then let us. I think we have already written. Then substitute for this sigma x at x by this and sigma x and delta x by this. Yes, by I. I take this term on the left hand side. Minus sign becomes plus. So minus becomes plus. So delta f zx, there is no need to take zx, I just have taken just to signify that this is z plane and this direction is x. It is a force, but then this is the correct direction, equal to plus, so I will take this one first, integral at a1 yes, these two, this is plus sign, this is negative sign. So this is x plus delta x, this is at x, negative one is at x. So that is written here, this is at x plus delta x. So I have just substituted the value of sigma x. Sigma x is this, and sigma x at x is this. I have just substituted, nothing else. Okay, then MMA integral r equal to, expand this, what is the length of the element? Dx. This element size, what is this element? What is this total length from here to here, here to here? Dx. So I am just dividing by dx. So if you divide this, take limit so you get equal to dm by dx. Dm by dx can be taken outside the integral sign. Because area of cross section, this dA consists of area of cross section. So dm by dx is not a function of z. also can be taken outside. I also can be taken outside the integral sign, and what will remain inside the integral is only ZdA. What is dm by dx? Rate of change of moment with respect to x. V, shear force. Shear force acting at the cross section x. So this is shear force V. Then 1 by I integral call this quantity ZdA. What is this? First moment of the area. It is area dA. What is dA? Sigma x is there. So dA is how will you consider dA? B into dz is dA. That dA multiplied by z from the distance from neutral axis. So it is the first moment of the area. It is not second moment of the area. Second moment of the area is moment of inertia. Second moment of the area is called this moment of inertia. This is first moment of the area. So this is something, have you come across this kind of quantity? First moment of the area? When? Where? Shear center. Shear center I have not taught yet, unless you have read on your own. First moment in physics, some course in physics. First moment of the area, tell me. So ZdA integral over area ZdA is first moment of the area. First when you find out center of gravity of any area, then you compute this. Yes, you always do that by supposing there is a complex area. So it is A1 multiplied by that distance, then A2 multiplied by that distance, and then total area multiplied by distance up to center of gravity. So this you equate. In finding out center of gravity, we require this first moment of the area. Yes. Let us call this quantity as Q. Q is a function of Z, by the way. So although it is a function of Z, but we normally call just by a letter Q. So it becomes, and this quantity on the left hand side, dfz by dx, it is the shear flow, total force divided by dx. So it is what? Force per unit length. Dx you have longitudinal x, force, width is still included, F, because this divided by this multiplied by width will be shear stress. B, if you multiply dx by B, then it will become shear stress. So it is not shear stress, it is force per unit length. So this is force, shear force, per unit length. shear force per unit length. This will denote by a letter Q, small q, Zx. So we'll now therefore we get one formula, Qzx equal to Vq by I. By the way, this quantity is called shear flow. Shear force per unit length is called shear flow, not shear stress. Shear flow, its unit is newtons per meter. It is newtons per meter. It is called shear flow. So shear flow at a distance z from the neutral axis is given by a simple formula Vq by I. You get it? That means now if you divide Qzx by B, then what will you get? Shear stress. Shear stress at Z. Denote that by tau Zx. Tau. Normal letter that is used for shear stress is tau. Tau or tau. These are all Greek letters. So it is tau tau or like this or tau. I don't know. Shear or simply because you are not dealing with so many shear components, simply tau, and therefore you get the shear stress at a distance z from the neutral axis is Vq by I B. So we have got a very good form. These two formulas are very, very important. That Q is equal to Vq by I. Shear flow is, this is important formula. And the shear stress is IB. That means it is a function of Z. It will vary depending upon the location of Z. So how to find out? Just like sigma x was a function of Z. Sigma x also was a function of Z. It was varying linearly through the depth. So this is also varying. Okay, so remember this.